off the back here. So I had to put it in there. Keep going.
Alrighty. So your graphs and networks. There's a bunch of stuff which is just definitions, and you really need to have those. I'd rather probably not go through exactly all the definitions, but you'd want definitions for degree, simple graphs, isolated vertex, a definition for a complete graph. Now all of these are just things that you probably want to have handy. For traversing a graph, you would want the definitions of a walk, trail, circuit, path, and cycle. And you can get those straight from the book, so there's not a huge amount of point me going through those, but just a reminder that that's really quite important. From the point of view of the skills that you need and the other stuff that we'd want to have gone through, it's very important that you can tell the degree of any graph, any vertex. So in this cute little example graph, the degree of any vertex is the number of edges coming into it. And it's not so much the number that matters, but whether it's odd or even. So on this little graph here, this is odd with a degree of 3. This is odd with a degree of 3. This is even. Sorry, that's a really dodgy pen. 3, odd. This one's 4. I know the loop is only one edge, but there's 2 edges coming into the vertex, so that's even. Remember, of course, our definitions of our graph. The line is the edge, the points are the vertices, and where we really need to use the degree is in the concept of Eulerian graphs. And so Eulerian graphs. The typical Eulerian graph problem is the Konigsberg bridge problem. Now we covered the Konigsberg bridge problem. It would probably be a good idea to recognize and be able to draw a graph of the Konigsberg bridge problem. The question that they asked in Konigsberg was, can you do a walk that covers every edge only once? So it's Eulerian if you can do a walk that covers every edge only once. And it's for Eulerian, it's required to be a circuit, so starts and finishes at the same vertex. The reason we need degrees for that is that the way we can tell if you can do this is all vertices have even degree. Now that's not the case in the Konigsberg bridge problem, because a bunch of them, in fact all of them, are odd. But the reason we talk about Konigsberg there is that's where this idea of graph theory came from. Our graphs can be semi-Eulerian, and for those you can do a trail, not a circuit. That means it doesn't start and end at the same vertex, but it still covers every edge once. For semi-Eulerian, you can have a maximum of 2 vertices of odd degree. And your trail would start and end at those 2 odd vertices. So that's one very important aspect of graph theory, that you can find the degree of any vertex and then use that to check if you can do an Eulerian or semi-Eulerian circuit or trail. Related to the Eulerian stuff is Hamiltonian. It's very similar, but with visiting every vertex. There's Hamiltonian paths and cycles. And in the same way as Eulerian, I had a circuit which started and ended at the same one, or a trail which starts one and ends at another. A path obviously isn't closed, whereas a cycle starts and ends at the same vertex. When you're giving these walks, you explain which vertex you go to by listing the alphabet of the vertices that you're traveling to. So A, B, C, D, A is one way of describing the path that you're following. I didn't do an example there. So Eulerian, semi-Eulerian, Hamiltonian, and whether it's a path or a cycle, you'd want to have definitions of that. I'm really just going over the concepts here. There's a very useful skills check at the end of the chapter on page 253, which you should do. Euler's formula is going to be the next big one that you need. And that is V minus E plus F equals 2. Euler's formula only works for connected graphs, planar graphs. So a connected graph, no vertex is off on its own. You can get to any vertex via a path, a walk. A planar graph, none of the edges overlap except if they're going through a vertex. And I'll draw a connected planar graph here so we can look at the example. So it's connected, there's no vertex off on its own. It's planar, none of the edges are crossing. And we need V for vertices, E for edges, and F for faces. Now vertices and edges are easy. There's 3 vertices. There's 1, 2, 3, 4, 5 edges. Faces are like the zones in the shape. So there's a face here, a face here, a face here, and there's the exterior face that's all around the outside of the graph.
Yeah, that's gay. I hate that, it's so confusing. So carry on.
Could we not use the concept of anyone's sexuality in a negative sense, please? And there's 4 faces. My apologies to anyone ending up watching this who heard that extremely offensive piece of homophobia.
What happened?
What this formula will let you do is you can confirm the formula. So I can go, hey, for this graph, v minus e plus f should equal to v minus e plus f should equal to 3 minus 5 is negative 2 plus 4 is 2. Yes, Euler's formula works for this graph. Or if they described a graph to me and told me how many vertices and how many edges there are, I could find the number of faces by substituting it into the formula. So that's Euler's formula. While we're talking about planar graphs, I might get really tricky and ask you to redraw a non-planar graph as planar. Because all I would need to do for this one is leave almost all of the edges in place and pick up one of the crossing edges and take it round the outside. And that's now a planar graph. Another concept that we might want with graphs is whether they are isomorphic. That is, even though they've been drawn differently, they actually have the same information. So these are isomorphic. I drew them differently, but nothing's actually meaningfully different about them. So for 2 graphs to be isomorphic, they both have to have same number of edges and same number of vertices. Vertices would have to have the same degree, and the edges would have to connect the same vertices. So I'd check, is there a line going from this one to this one? Yes. Is there a line going from this one to this one? Yes. So those can be isomorphic. You've got to have the concept of adjacency matrices and networks. Where, of course, you have a network, you can make an adjacency matrix, adjacency meaning next to. You put the names of each of the vertices down and across your matrix. And what this is saying is it's the number of edges from A to A. So that's no, there's none, but from C going to C, there's one edge because there's a loop. So if you see a 1 from C to C or from B to B, you'll know there's a loop. And then I've got one edge from A to C, no edges from A to B. And so your adjacency matrix will end up looking something like that. So, about the only other key thing is, for starters, you'll need to be able to use any of these to solve real-world problems. Such as if I said, Bob wants to travel to town A, B, and C and back to town A, but not cover any road twice. You'd have to work out, well, which of these major concepts are we talking about there? Is that Eulerian? Is it Hamiltonian? Is it a walk? Is it a cycle? I don't know, but you'll need to find that out. You'll need to be able to solve those. The last issue was the weighted networks. And that was when you have a value on each of your edges, and usually we'd do something like ask what the shortest way is to get from A to D. You would have to evaluate all the different paths. Sometimes we'd ask for the length of the path from A to B via C, meaning you've got to go A, C, B. Obviously, add up as you go. You would need to be really on top of the method for evaluating all the different paths. If I had to get from A to D, from A, I can go to B or C. If I go from A to B, that's 3, that's 2. Now, technically, yes, obviously, either of those would go straight to D after that. But if you want it to be incredibly thorough, if I've gone first to B, I do still have 2 options there. I could go C or D. C or D, and from C, I can go to D. So you're never being asked to backtrack. I'm not being asked to say there's infinite paths where I go A, C, B, C, B, C, B, C, B. Oh, now I'll go to D. But any vertex you haven't yet been to in that path is an option, yeah?
You know how you're saying weighted networks, if we were explaining it, do we have to set it up on the diagram on the left?
If you're trying, now if for something really easy, like if you can just inspect and say, no worries, but I'm doing an easy example to remind you what the concept is. So from...
Say if it wasn't an easy example, you wouldn't expect us to draw that.
If I expected you to show that you had definitely got the shortest path and what all the other path lengths were, I'd expect a diagram.
Yeah.
Yep.
So just to make sure that's in place of the...
That's in place of Dijkstra's algorithm.
Okay.
So it's the last one that we did. And this is the one that Mr. Allen taught me and I taught you. And so like he calls it Allen's algorithm, which is fine. He gets to do that. You put the weights of the path on it, so from C to D, and then you add up. Once you've got from A to D, so that path would be 8. This path here, A, B, D, that's only 5. Same from C, evaluate these. Sometimes there can be a path that's just so totally ridiculous that you don't need to put it in, and that's fine. But you would need to finish this and work out the shortest path.